There we go. Okay, so today, 2 weeks since we last met. In the meantime, my back has recovered completely from the operation, so I'm now going to be presenting on the board. I'm afraid that's not going to be as good for the video or for the people on Zoom, and I'm sorry about that. But still, this is my preferred means of presentation. I will still give some, so I suggest you take notes in the lecture, but I will also put some notes online, the notes that I'm working from. Okay, so before actually starting with the lecture today, just to say this is the first day we've got student presentations, and not all the people giving the student presentations are here right now, but they hopefully will be by 10 o'clock. So because of the student presentations, I'm going to structure the lecture a little bit differently. So we're going to have, so the structure of future lectures. Also, I should say, the student presentations, I think I will not put on Zoom because these are assessed presentations. It's nice to have people here in the class, but they're not going to be recorded, and I don't think it's right to broadcast them on Zoom. So the Zoom part will just be the lecture. Anyway, the structure of the lecture now and for the remaining lectures when we have student presentations is going to be, so 8:15 to 9 o'clock, and then just a short break now, 9:05 to 9:50. So here we're going to have two parts of the lecture, and then a 10-minute break at this point, and then 10 o'clock until however long it takes. They're supposed to be maximum 25 minutes each, the presentations, so ideally till 10:50, we're going to have the student presentations. So as I say, the lecture, this will be on Zoom and recorded. The student presentations just in the classroom. And I'm sorry I didn't announce this before. I should have done. Right. Okay. So after a week's break from the course, oh yeah, one other thing to say, we have to do an attendance today. This is the new regulations to do with COVID. So I shall put the lecture attendance, I think, in the 10-minute break here. I was trying to get it sorted out before the lecture. I didn't quite have time to get it set up. Right, so we've had 2 weeks break. So let me just remind you where we're at in the course. And the exercise is not just to repeat definitions here. I'm going to repeat some definitions, but I want to have them on the board anyway, because we're going to modify the definitions in a moment. But in any case, since we've had a week, since we had a whole week of break last week, it seems worthwhile remembering the basic definitions that we had. So we defined what it meant for a language. That's a set of strings to be in deterministic time of a function t of n that's counting an upper bound of the time. So we said that a language L was in d times of t of n. So that was if there exists, if and only if there exists a deterministic Turing machine, M, that decides L such that runtime of the Turing machine, so the time function of the Turing machine n, that takes a number n and gives us the worst runtime on all input strings of length n, so the maximum runtime of all input string n, that function is big O of t of n, so essentially bounded above by a constant multiple of t of n, more or less, apart from a few initial instances. So that was deterministic time. We also have the analogous notion of non-deterministic time, where the only change we make to the definition is that there exists a non-deterministic Turing machine. And the rest is the same, that decides L such that time m of n, so the time function in inputs of length n for the Turing machine n is again big O of t of n. The only difference now is that we need to be a little bit careful how we interpret the time function, because it's now the worst case runtime over all words, input words of length n, and also all possible runs of the Turing machine on all such words. And then, using these two notions of deterministic time and polynomial time, we define the class P, that's deterministic polynomial time. So this isn't exactly the same definition. I've given, like, I think 2 definitions already. This is not exactly the same, but it's equivalent to it. It's an easy exercise to show it's equivalent. So it's the union over all integer polynomials, well, natural number polynomials, of languages, sets of languages d time p of n. So it's all those languages that are executable in deterministic time of some polynomial function on the integers, and NP was the same thing, but with respect to non-deterministic polynomial time. So So the union over all polynomials of the classes of languages, the class of languages n time p of n. And of course, from that, we get that P is contained in NP, the language is decidable in non-deterministic polynomial time, then it's decidable, it's decidable in deterministic polynomial time, then it's a fortiori decidable in non-deterministic polynomial time, because the deterministic Turing machine is a trivial case of the non-deterministic one. Okay, so that's essentially where we're at. We've seen, yes, NP indeed, very much. So that's where we're at. We've seen examples of polynomial time languages, examples of non-deterministic polynomial time languages, and we saw in particular the satisfiability language, which is complete or non-deterministic polynomial time, and we saw what that meant. So, looking at how much time the computation takes is one way of bounding resources. Another way of quantifying the resources that a computation takes, we might say, well, we're not worried how long it's going to take, we can be very patient, but we've got only a limited amount of space on our computing device. So basically there are two major resources that computers use. One is time, how long you wait, and the other is space, how much space, storage space does the computer need. So it's natural to look at also space-bound here. And today we're going to do that. We're going to begin looking at space-bound, and we're going to extend this picture, and we're going to find a lot of other interesting languages. Sorry, not languages. Interesting complexity classes. So we're going to look at, just like we looked at polynomial bounded, deterministic polynomial bounded time, we're going to look at deterministic polynomial bounded space. We'll call that PSPACE. And the non-deterministic polynomial bounded space. And for the same reason that P is contained in NP, also deterministic polynomial bounded space is contained in non-deterministic polynomial bounded space. And we're going to show that this is related to the time hierarchy in the following way, that in fact there's an inclusion of NP in non-deterministic polynomial time is, well, polynomial space is more powerful than non-deterministic polynomial time, or is at least as powerful as any NP language that can be decided in polynomial space, which is good. So there's a sort of relationship between space and between time complexity and space complexity. Space complexity is more powerful in the sense that time complexity is less restrictive than time complexity. But of course, it's still interesting how long it takes to compute. Even if we're looking at the space, it's interesting how long it takes to compute them. So we're going to see that these classes here take at most an exponential amount of time to run. And this is on a deterministic machine. And of course, we can also consider exponential amount of time on a non-deterministic machine. And here we've got time, here we've got space, here we've got time. Actually, we'll see there are some, if we again switch to space here, that there are some languages that are less powerful than polynomial time that are also natural to consider. These are languages that take logarithmic space, which I'll talk about in a bit more detail later. And again, we have logarithmic space on the deterministic Turing machine, the logarithmic space on the non-deterministic Turing machine. So the blue part is what we've done, and I'm going to try to cover all the rest of this picture today. So we're going to get a whole lot of new complexity classes, but I'm going to begin with a branch off here, which is, I want to keep this the same color here, as well as the non-deterministic polynomial time. There's a very natural related class called co-NP. And the co-complexity classes, one would consider co-complexity classes whenever one has non-determinism, one would consider the code of the complexity class. I'll just define it in the case of NP, and then we won't consider it so much after that. But this, so I'm going to now motivate co-NP. So this is motivated by, firstly, a simple observation. Let's call it a proposition. So if a language is in P, that's a set of strings, set of words, then the complement of the language is also in P. So if the language is polynomial time decidable, deterministic polynomial time decidable, then its complement is also non-deterministic polynomial time decidable. So the complement is all those, so a language is a set of words, and the complement is all words that are not in the original set, all words over the alphabet that are not in the original set. The complement is obtained by considering the set of all words in the alphabet, sigma, and taking away, so using this as a set difference operation, taking away all the words not in the set. Okay. So if a language is polynomial time decidable, then so is its complement. And the proof is really easy, because if a language is polynomial time decidable, there is a Turing machine, deterministic Turing machine that decides the language whose time is bounded by some polynomial function in the size of the input. So given that deterministic Turing machine, simply swap the accept and reject states, and you get a deterministic Turing machine with the same time bounds that accepts a string if and only if it was rejected by the original Turing machine. So it decides the complement of the language. So the proof is simply swap accept and reject states in a polytime Turing machine, deterministic Turing machine deciding now. So this property, if a language is in P, then so is its complement. We say that P is closed under complements. So this says P is closed under complements. So then it's natural to ask, is NP closed under complements? So is NP closed under complements? So if we have a language in NP, such as SAT, is its complement, that's the set of all formulas that are unsatisfiable, is that also an NP, for example? And this proof, if you try to adapt this proof that you swap, accept, and reject states, that doesn't work for NP. Can anyone see why not? So if you've got a non-deterministic Turing machine for SAT, so then if we swap the accept and reject states, why does that not give us a non-deterministic Turing machine for unsat? Can anyone see that?
Because so it's just for one solution to false, but if you do it the other way around, you're kind of trying to determine that for all cases.
Yeah, absolutely. So the point is we're looking for just satisfiability, we're looking for just one satisfying assignment that makes the formulas true. And the Turing machine might be searching other assignments and it will reject those even for a satisfiable formula. And therefore, if we do unsat, those rejecting runs of a satisfiable formula will become accepting runs. And so you'll still be accepting some satisfiable formulas. So the problem is the unsat means on every assignment, the formula gets assigned false. And if complementing a non-deterministic machine, because there are some runs that say yes and some runs that say no, even if you swap the yes and no's around, you still on the same strings, you might still have some runs that say yes and some runs that say no. So this proof does not work because of non-determinism. Okay, so that proof doesn't work, and in fact nobody knows a proof that does work. So this is an open question. And so given that we don't know that, it's very natural to consider the complements of NP languages. So we simply define co-NP, the complements of NP languages. So this is simply defined to be the set of those languages. So L complemented for all languages L in NP. So it's that class of languages. And actually, we can show that it's hard to decide whether NP is closed under complements in the following way. So I'm going to write down a little proposition. So if NP, so if NP is closed under complements, then NP is not closed under complements, then P is different from NP. But that's obvious because P is closed under complements. So it's an obvious statement, but what it shows is that it's going to be hard to show that NP is not closed under complements. Might be easy to show it is closed under complements, but even that it seems very difficult. People believe it's not closed under complements. But while we're at it, what I want to do is this pattern, if something holds, then P is not equal to NP, is quite, the problem with complexity is everything hinges on the P equals NP question. Very few statements are proved outright. But what the best thing one can do, typically, is reduce unknown propositions to the P equals NP question in some way or another, and then you have an indication of how hard it is to determine to answer a problem. So this is one case. If NP is not closed under complements, that's going to be hard to establish because we can show that P is not equal to NP. And it's going to be similar here. Here we've got a hierarchy. I haven't defined most of these complexity classes yet, but even before we do, here we've got a hierarchy. It turns out that very little is known about which of these inclusions are strict. It's kind of conjectured that most of them are strict, but very little is known. And one way of saying that is that in some cases, we can prove that if we can show that the inclusion is strict, then P is different from NP. So I'm going to write down a few simple statements that one can show imply that P is different from NP. So if any statements below, if any of the statements below is true, any of that, then P is not equal to NP. So one is NP is closed under complements. Another one is that P is strictly contained in NP and in co-NP. So in the intersection of those two languages. So here I'm writing, I always write the equals if I mean less than or equal to. When I write it like this, I mean strict containment. People don't always adhere to that, so that means strict containment. That's not. People sometimes write this to mean less than, to mean a subset or equal to. So just to emphasize strict containment. Also, if NP intersect co-NP is contained in NP, or strictly contained in NP, or if it's strictly contained in co-NP, or if NP is different from co-NP. All these things are difficult to prove because they all imply that P is not equal to NP. And these are all relatively straightforward to check. Some of them are it's immediate, this implication. So I'm going to leave this as an exercise to think about. But the point is, that it's hard to establish strict inclusions here. So just to give you some feeling for this, so we know that SAT belongs to NP. It's an NP complete problem. It's not known if SAT belongs to co-NP. In fact, if it does, then NP equals co-NP. And we could likewise say unsat, the complement of SAT, belongs to co-NP, and it's not known if unsat belongs to NP. That would be the same statement. Almost the same as what I've just said, and writing it in a slightly different way. The language of tautologies belongs to co-NP. So a tautology is a propositional formula. So formula is satisfiable if there is one assignment that makes it true, one assignment of truth values. A propositional formula is a tautology if every assignment of truth values makes it true. So deciding if a propositional formula is a tautology, that's a co-NP problem. And it's not known. I'm not going to spend much time on this in the lecture, but it's not known if tautology belongs to NP. And this class NP intersect co-NP is also interesting because in practice, many problems have been shown to be in this class, and almost all of them have ultimately ended up being shown polynomial time decidable. So if a problem ends up in the class NP intersect co-NP, then with a lot more work in some cases, so primality was a famous one for a long time. That was known to be deciding if a number is a prime. That was known to be an NP intersect co-NP for decades, and only very recently, within the last 10 years, was it shown that primality is polynomial time decidable. And there are still a couple of problems that are known to be in NP intersect co-NP that are not known to be in polynomial time. I'm not going to define this problem, but just to give you a flag, problem in game theory about whether a game is winnable by even, say, for two players, even and odd for these games, but it doesn't matter. So winnability of parity games, and it would really be take us too far out on a limb, too far out on a limb, like an arm or a leg, too far distant from the course to define this, but just to give you, just to mention it, the winnability of parity games is in NP intersect co-NP, but is not known to be in P. It's one of the very few problems of this kind. Right. So I want to go to space complexity now and define these space complexity classes. The idea of space complexity is what we're going to measure is how much working space a Turing machine needs to solve the problem. So the reason we're going to just look at working space, the idea is that a Turing machine will get some input and then it'll do some work on some working tapes with the input and eventually come up with an answer, accept, reject, or maybe it's computing a string from it on an output tape. But we're not going to take into account the amount of space taken up by the input. And it's useful to do that to model scenarios in which you can think of having a computation in which you get the input from somewhere else, say off the web or something like that. You can access the input. It doesn't need to be stored. You might have your own device that has some limited space. You might be able to access the input somewhere else that it's computing on. But all it needs to do is it needs to keep its own working space within the space bounds it has. That input does not need to fit in the device itself. Okay, so the definitions are going to allow that. And that's useful because that then allows us to consider these classes here where we're going to look at logarithmically bounded space. And I'll talk about why this is important. We're just counting working space a bit later when we come to that in detail. So in order to do that, how much working space, we're going to so to look at how much working space, we're going to assume that a Turing machine has a special input tape. Special input tape, and this is read only. So it has a read head on the tape that can move left and right, but you can't overwrite this tape. It's not working space for the machine. And then it can have, say, K working tapes. and these are read-write. And then if it's a determinist, sorry, if it's a Turing machine that's computing an output string, in that case we need an output tape as well. So possibly we don't need an output tape if we're just deciding membership of the language, because that just decides by accept and reject states. So possibly we have a special output tape. And perhaps it's not so unsurprising that that's right only. So again, the output is not going to need to fit in the space of the computer, of the Turing machine. And then we define for such a Turing machine M, we define the function. So we have these functions here. How much time is taken up by a deterministic or a non-deterministic Turing machine? We're going to have an analogous function for the amount of space taken up by a deterministic or non-deterministic Turing machine. So for such an M, we define, maybe I'll put it here, just to make it more prominent. It's an important definition. So the amount of space taken by Turing machine M on the maximum amount of space taken by Turing machine M on inputs of length n is, again, the maximum over, and what we count for every run, we count the total number of squares that the read-write heads of the working tapes have pointed to during the computation. So there will be k such squares at the start, because they're all pointing, each k heads is pointing to one square, but through the computation they may move left or right or what have you. So for each of the k tapes we add up all the different squares that have been pointed to at some point in the computation by the read-write heads. So it's the total number. So I don't know if you know that NO dot is an English abbreviation for number for some reason. Total number of squares visited by working tape heads on run R. And that's over. So we want, so on runs R for every possible run of the Turing machine on an input W of length n. So we're maximizing over all strings from the input alphabet where the length of the string is n and where R is a run of the Turing machine and of input string W. There we go. And now, just to take us up to the first break, we can now define PSPACE and NPSPACE. And it's just the very natural modifications of the definitions of P and NP. So let's make the modifications in red. So we say a language is in better deterministic time, is in D space of T of n, some function T in the natural numbers, if there exists a deterministic Turing machine that decides the language such that the space function of the Turing machine is big O of T of n instead of the time function. Exactly what you'd expect. So similarly for non-deterministic space, again, there's a non-deterministic Turing machine that decides the language such that the space of the non-deterministic machine is big O of the function you've given it. And P space is simply those languages that are in deterministic space for some polynomial, and NP space is the languages that are in non-deterministic space for some polynomial. Sorry, I should be careful here. The complexity classes tend to be written in capitals, and in fact, in textbooks, they're bold or sometimes even in funny fonts. Whereas these are the main complexity classes, say, for polynomial time, whereas the specific complexity class for a specific polynomial, it's only capitals at the beginning and then lowercase. Anyway, so those are the definitions now. It's just once we've changed the time function to the space function, PSPACE and NPSPACE are just the natural definitions adapting time to space. Right, so it's 9 o'clock. I'm going to pause the recording and we're having a 5-minute break. Okay, so that was just a short break, but we'll have a 10-minute break, at least for those people who are not speaking, before the presentation. So, as I said, I'm aiming to finish my part at 9:50. Okay, so we've defined the classes of polynomial space-bounded computation and non-deterministic polynomial space-bounded computation. I'm not really going to talk about it much today, but let me just define L and NL, the logarithmic space-bounded computation. So there the definitions are similar. So L is the deterministic logarithmic space-bounded computation. So this is deterministic space of log of n. So in this case, you don't need to specify the base of the logarithm, and we don't need to union over any classes, because if we change the base of the logarithm, as you did in an early exercise class, any one base logarithm is big O of another base logarithm. So you get the same complexity class anyway. So simply, all we need to say, because we've got the big O in the notion of D space, already, it's just enough to make the logarithmic space bounded to be space bounded by a computation that's logarithmic in the working space, but whichever log function you choose. And as I said, I'm only going to use the log notation when it's irrelevant what base we use, and this is an example where it's irrelevant. What's interesting about this is that this is a complexity class that really only makes sense for space, not for time. It doesn't really make sense, although, I mean, there are restricted situations in which one can make sense of it. But in general, doesn't make that much sense to restrict a computation to logarithmic time, because then you can't read the input string. This is logarithmic in the size of the input, and normally to do anything interesting, you want to read the input string. But on the other hand, it does make sense to read the input string, which takes already time O(n) in the size of in the length of the input string. It makes sense to read the input string and then do computation that only takes logarithmic amount of working space on top of that. So it's not a very interesting notion if you try to do it with time, but it is interesting with space, as we shall see, but not today. And NL is just the natural logarithmic one. Okay, so I want to now look at relationships between space-bounded and time-bounded. So here we've got the logarithmic space-bounded languages, the polynomial time-bounded languages, the polynomial space-bounded languages, the exponential time-bounded languages, which I still haven't actually precisely defined these classes here. How do we get this sort of interleaving here? I'm going to focus on one particular example, which is showing that NP is a subset. So non-deterministic polynomial time, any non-deterministic polynomial time language is a deterministic polynomial space language. So first, a remark, which is that it's obvious that P is contained in P space and that NP is contained in NP space. So why is this obvious?
Because if you have an algorithm that only writes so a character on the output, so on the tape, we with the size of the word at the end on the output with the polynomial one. Does that make sense?
You might be saying the right thing. I'm not completely sure. It sounds.
Between a sheet of made polynomials, at most as many moves around the tapes.
Yeah, that's what I was looking for. Yes. So to move the head takes one time step. So you've got k heads, but that's just a constant factor. So in a certain amount of time, you can't see more squares than a constant multiple of the amount of time you've taken. So if you're polynomial time bounded, well, you can have only looked at polynomially many squares in the computation. So these inclusions are just direct by just considering the same Turing machine that you've got for to show that the problems in deterministic polynomial time show it's automatically polynomial space bounded. So that's obvious, but this inclusion is not as obvious. So we'll call this a proposition, not quite a theorem. That NP non-deterministic polynomial time is a subset of deterministic polynomial space. So to show this, suppose we've got an NP language such as that, but any NP language will do. What we need to show is that there's a polynomial space-bounded deterministic polynomial space-bounded computation. It's not immediately obvious because although on any run of this non-deterministic Turing machine, the space will be polynomial bounded, there are exponentially many runs potentially, and so you want to know that those exponentially many runs don't in some way require space. If one makes it deterministic, you can somehow reuse the space again in some way. That's one way of thinking about it. But it's actually not that hard to prove that, that if the language is NP, then there's a polynomial space-bounded computation. And I think the easiest way to do it is to think about the certificate characterization of NP. So by the certificate characterization, of NP, there exists a deterministic p time n, and the polynomial natural number polynomial, which is giving us size of a witness, such that a word belongs to the language, so a string is accepted, if and only if there exists a witness of exactly size p of n, such that the deterministic polynomial time Turing machine checks that the witness is a certificate for the solution of the problem. So if and only if there exists a v of length p of n, such that m accepts. So in previous lectures, I just simply wrote VW. Actually, I would have preferred to write it like this, where V hash W, where hash is a new symbol in the alphabet, and you're using it as a separator to separate the certificate from the word. It doesn't make any difference really. It's just somehow, if you would just run the certificate and the word together, you have the awkward question, where is the boundary between the certificate and the input word? So it sometimes makes sense to put a separator symbol in. Doesn't really change the definitions. So given this deterministic polynomial time Turing machine that checks witnesses, we can adapt this to a deterministic polynomial space Turing machine that just takes the input W. So we build a PSPACE Turing machine for L by so the Turing machine is going to do the following algorithm. It's a determinist, sorry, I really wanted to emphasize it's deterministic. So the way it works is, oh, by the way, I'm sorry that the screen's not up. I hope that, but this was the problem. So it's not possible to stand it. So this Turing machine is going to input a word W. So the algorithm is input a word W in sigma star. And then it goes into a loop where it repeats for every possible witness V. So it counts the length of W, and then it goes through every possible witness V of length P of the length of W. That's a sigma there. So we're going to carry the loop, checking every string of this length to see if it's a witness, and it simply write V hash W on the working tape. And then once we've written V hash W, we run M on the deterministic polynomial time Turing machine on the working tape. And if M accepts, then it means we've found a witness V showing that W belongs to L. So W is in the language. So we accept W if M accepts V hash W. Now this is a very time inefficient computation because it goes through every string V of length P of the length of W, where P is some polynomial, and there are, well, size of sigma to the power of P of length W, that many strings. So it's an exponential time computation, but it only takes polynomial space because it takes this much space, the space we take to write V and W, and this is polynomially bounded in the size of W, and then applies the Turing machine, deterministic Turing machine M to that, which is polynomial time and hence polynomial space bounded. Okay, and then once it's done that, it erases the V and it starts again. So it's just reusing the same amount of polynomial time, polynomial space over and over again. So it's inefficient. So this takes exponential time but is that only polynomial space. Okay. So I've already now mentioned exponential time. Perhaps I can use the middle of the board. So let's define, having mentioned exponential time, let's actually define exponential time and non-deterministic exponential time. And this is, by this point in the course, quite routine. Again, we're considering now time complexity classes. So if it's a space complexity class, we tend to put space in the word, except in the case of logarithmic, because as I said, logarithmic time doesn't really make sense. So there we don't need to put space because we can only put space. At least that's my own understanding of the rationale for the naming conventions that have been adopted. So exponential time is what we ask is for those languages that run in deterministic time bounded by an exponential of a polynomial, but an exponential whose exponent is polynomial in the size of the input. So it's the union over all polynomials of problems run in deterministic time bound that are of big O of an exponential. We use 2 as the base of the exponent, 2 to the power of P of N. And non-deterministic exponential time is the same thing. Of course, with non-deterministic time, non-deterministic Turing machine. Just to say, if we replace 2 with any other constant strictly greater than 1, it doesn't change the definition. It's easy to see that and leave that as an exercise. So 2 can be replaced by any C greater than 1. And it's the same complexity class, it doesn't change. Okay, so where I want to take us to next. So it's clear that exponential time is contained in non-deterministic exponential time. So the main result of the lecture is going to be that non-deterministic polynomial space is contained in exponential time. And this gives us an upper case, well, a worst case time bound for problems in NP, because they're also exponential time. If we want to know how bad is it, I mean, what's the worst we can expect for a deterministic algorithm for an NP problem with a time bound, or we can at least fit it into exponential time. We don't need to go to something worse than exponential time. There are worse categories afterwards where we can go to doubly exponential, where we put 2 to the 2 to the P, or there are lots of even more horrendous time bounds than that. But for these nice problems like non-deterministic polynomial time, non-deterministic polynomial space ones, we can always fit them into deterministic exponential time. That's a nice fact. It's the world is bad, one needs to wait a long time, but it could be worse. I mean, at least we know these problems fit here. And so the big result now, the remaining results. So let's start here. Let's see, do I want to do this now? Yeah. So this deserves to be called a theorem. So actually, just to say before getting started, it's not hard to see that non-deterministic polynomial time is that's contained in exponential time. And essentially, that's already shown by this proof here, because the idea is this algorithm, you always have it available for a problem in NP. You always have the witness characterization of a problem in NP. And you can always turn that into an exponential time algorithm that searches through all possible witnesses. So this inclusion that NP is contained in X is essentially that observation. But that's for non-deterministic polynomial time. But the non-deterministic polynomial space is not as simple as that. because we don't know how long non-deterministic polynomial space. We don't know a priori how long they're going to run, and we don't have in general this witness characterization. If we had a witness characterization, if we had small witnesses, then we would be doing, well, NP is exactly the class of languages for which we have polynomial bounded witnesses. So we need a different approach to establish the non-deterministic polynomial space. For any problem that's decidable in non-deterministic polynomial space, is decidable in exponential type. So let's prove this. So what have we got to go on? Well, we're going to have a language that's in non-deterministic polynomial space, and the proof, let's assume we have a non-deterministic Turing machine. Suppose M is a non-deterministic Turing machine deciding L. Whose space is bounded by, whose working space usage is bounded by a polynomial in the size of the input.
Hello.
That's okay. You're at least not late for your presentation.
Yes. My partner too.
I hope so. So what we're going to do is think about, so we've got the space usage is bounded. Think about what happens on a run of this non-deterministic Turing machine when we run it on a word W. So maybe come back to this board. In any run of M on input W, and it's a non-deterministic Turing machine, so there might be many different runs of the Turing machine on input W, depending on which non-deterministic choices are made. But what we can do in any case is consider, so a run is a sequence of configurations of the Turing machine. So let's consider what kind of configurations we can see. So every configuration encountered on the run has, well, I'm just going to repeat what a configuration is. So a configuration is a state. Now this is a non-deterministic Turing machine showing that it belongs to NP space. So it has this special input tape because it's an appropriate Turing machine for looking at space bounds. So it has W on the input tape because the input tape never changes, plus a head position for the input tape. So in any configuration, the head position will be in a certain place. And then we've got k working tapes. So we're going to have k different strings on the working tapes. And the space is bounded by the polynomial P of n. So in every working tape, well, we can only use less than the whole of the space, but we can think of the relevant positions on the working tape as being the relevant, strings on the working tape as being given by a string over the tape alphabet of length P of n. So most P of n squares can be used, actually not even up to P of n, but anyway, something strictly less than P of n squares can be used. If we look at the tape alphabet, we've got blanks as well. So we can pad it out with some blanks. And the relevant portion of each working tape would be a string where VI is the string over the tape alphabet, not the input alphabet, to the length of P of n. And again, plus k head positions. And we don't need an output tape because we're looking at a decision problem. So we have accept reject states, we don't need any output. In such a configuration, how much information do we need to encode it? Well, so you need some number of, let's encode it as binary bits. We need some number of bits to encode the states. It's a finite set of states. The length of W is fixed because that's our input. We need the head position. So that's like log of W to record the head position, or we can instead of record it in the length of W bits. I mean, we don't even need that amount. And each of these, well, depending on the size of the tape alphabet, but each of these, we can consider the smallest sequence of binary strings that allows us to encode every symbol in gamma. And if it takes like m binary symbols to encode a symbol in gamma, then each of these can be represented by m times p of n bits. Plus we need the head positions, and actually one way of representing the head positions is by inserting a special head symbol in the tape. Another way is to double the alphabet and also have a special symbol for this is the symbol with the head on this square. There are many ways of doing it, but what I want to say is that this doesn't matter how you do it, this information can be encoded by a string of bits. String or word. So let's call the configuration capital C, and I use these little corners for encoding for the string. So we can encode it as